Hello everyone, welcome to today's session. My name is Wycliffe, and in this video, I'm going to share with you how you can calculate the area of a water body, like the whole of this Lake Victoria, using Google Earth Engine in R. So let's get started. Okay, so we will start by loading the library. So I will say library RGEE, and then the other library we will load is map edit, which helps us to digitize the borders of the lake. And then we'll initialize our Earth Engine session, right? Okay, so after that, we'll draw using our using draw features function from map edit. We will draw our region of interest, and then we will convert that SF object to Earth Engine object so that we can use it for clipping our mapping area. All right. So to clip that, we'll use this drawing toolbar, and then we try to be as close as possible to what we can see as the extent of the lake. Yeah, like that. For your case, you might be more accurate. Okay, so after getting the region of interest, we will start by considering which image do we want. So I will use normalized difference water index from Sentinel to image. So we'll say Earth Engine, image collection, and then datasets, and then we will look for S2SR, okay? Harmonized image, that is image from Sentinel-2 surface reflectance. And then because it is cloudy, it's affected by cloud, we will remove the clouds using CloudScope Plus package, collection, sorry. So we need image collection, and then we look for dataset, and then from dataset, we look for CloudScope, okay, that one. After we gotten the CloudScope, we ask yourself, when do we want this? So let's say we want it for 2024 alone. And then the end date, we will start filtering our image collection from 2024 to 2025. So that means when all the months of 2024 shall have been collected, the filtered, then 2025, it will stop. So there will be no 2025 image filtered. All right, so our S2 will get S2, and then let me remove that. Okay, and then we filter bounds. We filter bounds using our region of interest, and then we filter date using start date and end date. Okay, after filtering for the date, we can then link our collection with CS Plus. So because that is the collection that has a CS Plus, that has CS band or CloudScope band, which we can use to filter each of the images in our collection, okay? So we will map a function, and the function should take an image. After taking an image, we get the quality assessment band, which is from the image, we pick the CS band, okay? After picking the CS band, then we have our image, which will be the image, but then we update mask, or we mask out, right? We mask out where the quality assessment band is greater than 0.6. So those are considered cloudy images. After that, we get our image back, and then we copy properties, right? We copy properties so that we have the system time start. From the image, copy Earth Engine list, and then we provide as a list the system time start. So this will help us to index our image, okay? Then after getting the images which are now clean and have a time property, then we can now map a function to calculate the NDVI, okay? So we will map a function which takes an image, and after taking an image, we pick the necessary bands. So this will be the image. From the image, we select 2 bands. So we provide them as a vector here, and that will be band 8 and band 3. So we can say pick band 3 and band 8, okay? After picking them, we can normalize them. This is not compulsory. We can normalize them using a scale factor of 0.301, okay? If you check, sorry, S2 SR, this harmonized image, then under bands, band 3 and band, sorry, let me expand it. Band 3, sorry, it's here. Bands 3 and band 8, both of them have a scale factor of 0.301. Okay, so that's what we use to multiply them. Anyway, if we are calculating NDVI, then we are not even concerned so much about the normalization. Okay, then, sorry, NDWI. This is a normalized difference water index. So it's an index which helps us to detect water bodies. Okay, so we'll use normalized difference function, and then to the function we provide the 2 bands. But now we must be very careful that we provide the bands in the right order. So we should not start with band 8, then band 3, but we should start with band 3 and then band 8. That is the near infrared and the green band. After taking the green band and the near infrared band, those are the bands that we use to calculate normalized difference water index. And then we rename our index to NDWI, okay? After that, we need to copy properties if we wish. For this, we just wanted the median, so we could go away, get away without the properties, but it's a good practice. So we copy properties, and then we get them from the image, where the image, we get it from a list. From the image, we pass it to a list, the list of system time start. So that is the same function we had up here, system time start, okay? Like that. So after that, then we have clean images for NDWI only, and then we can get the median image for this one here, okay? So we can run that. I hope it ran well, no error. Then after getting that S2, we can even print it to confirm that we have our S2 images. Oh, in R, we use EE print to see the details of our Earth Engine object. That might take a bit of time because we have so many images, around 74 or even over 74, because this could be stretching beyond the 2 tiles. Okay, so we have our normalized difference water index as one image returned, which is the median for the whole year, right? So if you want, for example, to know how the extent of Lake Victoria in the year 2024, because the extent can change. Water can swell, water can reduce, and so forth. Okay, so let's get a threshold on this normalized difference water index, right? Because normalized water index detects better water if its value is above 0. So we will provide a threshold where we say, look for areas where our normalized difference water index is greater than 0, for example. This is preferred threshold so that it whatever it's above is above 0 with NDWI is normally a water body. So it can help us to get areas by thresholding that are water bodies, okay? So then let's see which areas those are. So we'll add layer and we add this threshold. Actually, this is a binary, so we can get the NDVI image itself. So we can say NDWI or mask, yeah. We can get it from threshold and then we update mask or we self-mask. Yeah, for this case, we self-mask so that we get the actual image. Okay, so we will provide this masked image for the water body itself now, and then we clip it to our region of interest. So we use $, because it's an image, we can clip it to our region of interest, which we drew, and then we can provide visualization parameters, which we can provide as a list. And since it's just everything will be one value, then we can just provide a single color, like palette is blue, for preferable for water body. Okay, let's see. Let's see what we get in Lake Victoria. It's taking some time because this is a 10 by 10 meter resolution, and Lake Victoria, I think, is over 60,000 square kilometers. So you can imagine how many pixels it's struggling to get here. Yeah, so these are this is the extent of Lake Victoria as of 2024, according to the water index. Okay, you can see some white places inside the lake. Those are masked out. Those are islands. They are not water bodies. Otherwise, the rest is water body. Okay, so don't worry when you see some empty spaces and you're like, is this misleading or something? Okay, so once we get our water body, we might be interested in knowing the area. Yeah, it's not just getting the lake, the mask, but also calculating the area of this. Okay, so to calculate the area of this, we can get Sentinel, let's say pixel area. We create a pixel area image, which is just the mask. Then we calculate the area of each pixel, right? So from this mask, we will multiply it by Earth Engine image. From Earth Engine image, we get the pixel area function, right? Pixel area. So for the pixel area, we will get the area in square meters. So we can divide it by 1⁶ to change it into kilometers squared. So divide by 1e6. Okay, so that gives us an image which has got areas of each pixel. So we can add all of them, all those pixel areas to get the total area of the lake. Okay, so lake area, we can create an object called lake area, will be the images with pixel areas, right? The images with pixel areas, and then we reduce region because we have a geometry. So our reducer, we can use a reducer sum, of course, because we want to add all the areas, reducer $sum. So we want to add all the areas, and then geometry, we want to do this reduction over our region of interest, and then scale. Now this is where we need to be careful. If I put a scale of 10, we are going to see an error. Okay? Even if we provide best effort as true, we will still likely get an error. Okay? And then after getting that, okay, let me just try it and confirm that we are likely going to get an error here. That returns an Earth Engine dictionary. So from the dictionary, we can get values and only get the first one. Okay. Get the 0th object on this. Okay. So I suspect Why is this still returning an Earth engine object? Get info. Yeah. So we get information from that Earth engine object. Okay. Yeah, this is likely to throw an error because Lake Victoria is such a huge lake, probably the largest freshwater lake in Africa. User memory exceeded. So, okay. So we increase the scale so that the aggregation is done at 1 kilometer. And of course, even that, we still have around 70 pixels to work with. Because, yeah, over 70, because the area of this lake is, I think, around 70,000 or so square kilometers. Such a huge lake in Victoria. So our computation is done and we have around 65,000 square kilometers, okay? So we can also check what is the area of Lake Victoria. 68,000 square kilometers. So online, we are getting such kind of value. And in R, we are getting 65,000 for that year. So we are quite close to the actual area of the lake. Okay, so what have I shared with you today? I've shown you how you can use normalized difference water index, NDWI, with high resolution Sentinel-2 image to calculate the surface area of a water body. It doesn't have to be a lake. It can be a dam. It can be any pool of water. Or if you want to detect presence of water in some location or flood that has occurred in some region, if it coincides with the passing of this Sentinel image in a cloud-free day, then or period, then you can get the area of region affected by the flood where water can be seen from the space. Okay, so if you like this video, please share it with your colleagues. You are free to subscribe to get more of this kind. And feel free to cite accordingly the sources of data that you have used and packages like MapEdit. These people have done a great job. Otherwise, we would not be able to digitize a polygon around this if they were not there. RGE, great work connecting us with the Google Earth Engine and enabling us to pipe it in our comfortable R environment without any pressure. Okay, enjoy, happy coding. This script, I will leave link to it in the description to my GitHub repository from where you can access all content of this workflow and apply it in your own region of interest.